So our next talk is from Jocelyn. She's going to talk about automated translation of functional big data queries to SQL.
Thanks for the introduction. So I'm Jocelyn. I'm going to present this paper for my colleagues on automated translation of functional big data query to SQL. So the joint work with Guoqiang by Mariano, Xipeng, Shen, and Işıl Dillig. I'm not on the paper, by the way, so yeah. So first of all, let's start with what is functional big data query. So functional big data query, let's look in the context of example, is a program that looks sort of like this. A functional query is composed of invocation to second-order APIs, such as flat map, map, and reduce by key. These APIs usually take first-order UDFs as argument. The UDF are written in general programming languages, such as Scala and Python. The good thing about functional big data query like this is that they're very expressive. You can see, like, for example, the UDF you can use whatever programming language you like. However, it's very less performant than SQL. So to get why this is the case, let's look into a context of example. So here, we want to have the input table have two columns, last name and the first name. I would like to write a query that generates an output table where the first column indicates distinct last name in lowercase. The second shows how many people have the same last name. And lastly, what is the length of the longest full name for each of the distinct last name. Here, I show you the program that will write in order to take this input table to this output table in both Apache Spark program and also SQL query. So as you can see that, the first thing I would like to highlight actually is that SQL query here is 11 times faster. So furthermore, the two programs actually compute in the output in a very different way. Consider the diagram in the bottom of the screen, which shows the execution of the two programs on a particular input. The top part here over here shows the execution of the Spark program, and the flow down here shows the execution of the SQL query. So for the Spark program, it first converts the last name to their lowercase, and then group all the user by the last name. By the last name, it then maps those users to the last two columns by getting a size and max length. On the other hand, the SQL program works very differently. It first casts each last name to lowercase and compute its length of the username by summing the first and last name. And then it groups the user by last name and takes the maximum of the full length. So you can see that not only these two programs look very, very differently, but they're also very different in semantics. So this imposes a huge challenge in terms of when we want, given a Spark program, how do we convert into a SQL query that hopefully to be much more performant? So our solution is to rely on a concept that we call column-wise decomposition. The goal for this example is to design a program that can produce the table on the bottom given the input table on the top. Our central idea is to synthesize three different programs, one for each single column, and then merge them together to retrieve the final program. Here, as you can see there, on the left, we synthesize three different separate SQL queries for each of the columns, and finally merge them back together to get the full program. In order for this approach to make sense, there's a key thing that we need to verify to be true. First, synthesizing each single column queries should be much more efficient than synthesizing the full program query. And second, merging them must be really efficient. So are these things true? So in order to, well, of course, these are true, but these are true based on two key observations. Our solution relying on two observations, and first, queries for individual columns of the output often share very similar structure. And second, queries that share a similar structure can be easily merged. To give you an intuition for why this is the case, let's look at this example. On the right, I show you the full query we would like to synthesize. And on the left, I have pictured 3 column queries, which each produce one of the 3 expected column output. On the initial inspection, hopefully you can come to the conclusion that these column queries look somewhat very complicated. However, if we take a closer look, we realize that large part of the column query are actually shared. Only the portion I outline over here actually differ between various column queries. This is the heart of our first observation, that much of these column queries are actually the same. Additionally, we notice that we can actually construct a full design query by keeping the shared portion of the column query and then concatenate them together, the remaining portions, and this corresponds to our second observation that the column query with this structure can be easily and efficiently merged. We operationalize these observations in an algorithm that takes advantage of what we call a dependency-free query sketch, or DFQS for short. A DFQS is a partial SQL query which takes two key properties. One we call a syntactic property, and one we call a semantic property. The syntactic property restricts where hosts can appear in the program to only projection aggregation operations. The semantic property ensures that complete sub-extraction of DFQS must evaluate to the same value on any completion of DFQS. While this definition might seem a little bit complicated, each part of the definition serves a key role for our algorithm. The syntactic property ensures that column queries can be efficiently merged into a complete query. Meanwhile, the semantic property is the key to ensure that our efficient merging procedure will always produce the correct complete query. Here you can see a DFQS that is used for our running example. This query has both of properties listed above. Okay, so now we understand the general idea of DFQS. How do we put it into a synthesis algorithm? Our algorithm starts by splitting the functional query into one functional query for each of the column. These programs can be trivially obtained using the map operator of most functional query language to retrieve the ith column. So suppose in this case I have a table with n column, we have 1 to n columns separately. Then, each column function query is passed to a counterexample-guided inductive solver along with the DFQS produced by the DFQS generator. Anytime that any column query, since this problem fails, the DFQS generator is queried again for the next DFQS, which is then sent to the CGIS solver of the new column queries. Eventually, when DFQS is found such that all column queries can be successfully synthesized, those queries are merged together to produce the final desired query. Because we have limited the query to be instantiations of DFQS, we can efficiently syntactically merge these queries. We now know how we can operationalize the DFQS in an algorithm, but it leaves the last important question to answer. How can we efficiently enumerate DFQS so that this approach is actually efficient? Well, the way we do that is we adjust the algorithm that we showed previously. And in this new algorithm, we first synthesize one of the column queries at random. You can be any columns with no DFQS. Then we pass this generated column query to a DFQS extraction algorithm that extracts DFQS from a column query. Intuitively, this procedure keeps a concrete sub-expression of the query that are necessary to maintain the desired properties of DFQS and replace all the other hosts with hosts. Once the query sketch is generated, it is used as a DFQS for all the other synthesis problems for the rest of the column. If any of the column synthesis problem fails, the synthesis procedure for the base column, the one we start with, is invoked again and to produce a new column query and a new DFQS. This process continues until a correct column query is discovered for all the columns, at which point the results are merged and the final query returned. To assess how good our approach is, we built a tool called RDD to SQL and evaluate on a benchmark set we collected. To collect the benchmark, we download all GitHub repos with at least one start and one call to the Spark RDD API. We then extracted all non-trivial programs from this set and randomly sample 100 programs. So here we show some statistics of the gathered program shown on the bottom of the slides. And as you can see, it's fairly complex in terms of line of code and ASD size. The first question we want to answer is how well our proposed synthesis or transpilation algorithm works. So this graph, we run all the benchmark within a 1-hour limit. The graph shows the percentage of benchmarks solved on the y-axis and the time it took to solve on the x-axis. As we can see, RDD to SQL can solve 98% of the benchmark within the time limit and actually solve most of the benchmark within the first 7 minutes. We also compare RDD to SQL to two different extensions of CLIS, an existing synthesis tool for query optimization. The graph here shows the number of benchmarks solved on the x-axis with the cumulative synthesis time in seconds on the y-axis. As we can see from the graph, neither of the extensions of CLIS can solve nearly as many benchmarks as RDD to SQL. Lastly, remember that the motivation of doing this whole translation from RDD to SQL is that we want to get more performant query. So how performant is actually the query that was synthesized? So we evaluate how big a performance gain we can achieve using the synthesized query as opposed to original ones. The average speedup of the synthesized query was 2 times with the maximum speedup of 7 times across a variety of cluster size and randomly sampled inputs. So in this talk, I discuss our algorithm for automatically synthesize SQL queries from functional big data queries. I first explain the problem and motivate why this is challenging. Then I also explain the key idea before our algorithm, column-wise decomposition. Then I explain our synthesis algorithm, which solves the problem by decomposing it into individual translation problems for each of the column. Finally, I show the result of our prototype implementation called RDD to SQL, which indicate our algorithm can successfully transpile a variety of queries, and our algorithm is able to transpile many more queries than other related work in the literature. Thank you so much, and happy to take some questions if I can answer them.
Questions? Go ahead.
Hi, thanks for the talk. I was just wondering, so your input is kind of arbitrary functional programs.
Yes.
So do you have any kind of statement about the completeness of your technique? Under what conditions can you actually generate SQL? Is there some sort of restricted subset for which that's practical? Have you thought about that? Thank you.
Okay, so I think that's a good question. And in terms of completeness, I'm actually not sure for arbitrary function query, you can actually do that. But I think I asked the author for that, so I give you the answer I get a while ago. And it seems like, they collect a couple very commonly used from GitHub, and I think they're able to synthesize from a SQL from those queries, and they are correct. So in that sense, it should be probably there's no completeness guarantee for any functional queries, but for common one, it should be sufficient.
Okay. So are there any queries that sort of compile to joins in SQL?
Sorry?
Are there any functional queries that compile to joins? Like joins?
I think so, yeah.
Okay. Could you give me a statistic on what proportion of these are join queries?
Oh, that's a great question, and I have to refer you to the paper.
Okay. Fair enough. And one more question. So with respect to speedups, so what are the speedups in relation to? Like there are 8 machine ones, 16 and 24.
Yes.
So these are speedups of the compile SQL with respect to the original.
Yes. Yes,
okay.
Exactly.
And how was the SQL executed across? Like, what was the runtime for SQL to execute across 24 machines or so?
You mean how long the SQL execution time is?
No, I mean in general, the SQL runtime is single database or single thing, right? So how was it distributed across 7 or 24 machines?
I actually don't know, and you probably have to ask the author again.
Thank you.
Yeah.
More questions? Okay, let's thank the author.